yeah. So if you don't have any more questions, I prepare a very interesting video for you. Then from this video, actually, you can get a very good sense of how these algorithms are working and how their performance differ from each other. Sounds weird, right? Because it's a very cool video, and you can find it on YouTube. I love it personally a lot. So are you ready? So this video is called, hi. And this video is called the 15 sorting algorithms in 6 minutes. In this video, each of the columns here are a number to be sorted. So our goal is to sort this stuff into increasing, numbers, right? And this sorting algorithm will be included in this video. So let's sort them one by one. And according to the process of the sorting, you can see how different algorithms performs differently. Especially some of them are much faster than the others, right? So let's see. So the first one is selection sort. Selection sort is a constant order n squared time. You see that? Those red columns are the ones being swapped. So finish. Cool. This one is the insertion sort. Insertion sort in the best case is order n, but usually it's order n squared. We are inserting every number into the pre-sorted sequence. So insert everyone into it. Getting slower because the sequence to be inserted are getting bigger. So it's keep getting slower, but it will finish at the end. The third one is quick sort, right? Split it half, split. Then bottom up. Split, bottom up. Okay, pause a little bit. If you notice, in this algorithm, the demo are actually much more samples from the previous one. See, the width of each sample is very narrow here. Because in the same time, quicksort can sort much more elements than the previous sorting algorithms. So, because, there are much more numbers here compared with this one, right? Very clear the difference. So, then I can finish this. Then build it up, bottom up. Much more powerful than the previous ones. This one is a merge sort, right? Merge sort is a constant order n log n, right? Sort the subarrays, merge, subarrays, merge, and then merge. Also very quick. And next one is heap sort. Heap sort, these colors here are actually showing which layer are the elements now in the heap. Right? Keep popping from the top, and then add it into the already sorted ones. From the from the root of the heap to the leaf of the heap, then keep popping. Heap sort. This one is the radix sort we just mentioned. It's very straight using binary digits comparisons. So it's fancy. Cool. This one is another version of the radix sort. And in this one you can see in the middle of the sorting is more like a already sorted thing. This one is the standard sort in the GCC library, how they work. We can see that it's actually using some randomized techniques to improve the performance. They are just firstly sort it roughly, and then clean it up. That's the built-in GCC sorting algorithms works. This one is the GCC built-in stable sort. For a stable sort, it means that in the worst case, it will still perform pretty good. And if you see that this one is very close to one of the algorithms here, so which one? Can you find it out? This one is similar to the merge sort, but the sequence is a little bit different, right? But it's some sort of adjusted merge sort, which is stable. Because we see that the merge sort are guaranteeing an n log n. This one is the shell sort. See the steps are keep getting narrowing. These steps are keep getting narrowing, and then from a roughly sorted array to a dedicatedly sorted array to a fully sorted array. Shell sort. This one is bubble sort. See, a bubble sort can only sort this many of elements. Is the ability is not that good, but it can still sort things. So bubble sort. This is an interesting one called the cocktail shaker, like you are shaking something. So you're getting the top elements here and the least elements here. So every time find a max, find a mean, and then finish the thing. This one is the genome sort. It's a very strange sort, but it's similar to the insertion sort. Yeah, it's something similar to the insertion sort, but with some variations. If you're interested, you can cover it after class. You're not required to know all these following algorithms, and this one is called the Bitonic sort. It's also based on some binary roots. You can see it's very strange, but finally it works and it looks very quick. This one is my favorite sorting algorithm. It's called the BOGO sort. This one is my favorite. So okay, can anyone guess how does the BOGO sort works here?
I have no idea.
So
is it sorting?
good point. Is it really sorting? But it's called a BOGO sort. So any idea? What is this stupid sorting algorithm doing? What is it doing?
I don't know.
Okay, so firstly, this algorithm is called a BOGO sort, and actually no one is using it, but it is an algorithm. Okay, listen, the algorithm is like this. So we have an input array of elements, then we generate a random permutation of it. A random permutation of it, like this one. Then check whether it's already sorted. If it's sorted, output. If it's not, random permutation again. See that? That's like when you're having a pile of papers, you want it to be sorted, you just push it, and then see whether they are already sorted now. And then you gather it and make a check. Okay, it's not sorted. Then do it again. So the time complexity for this algorithm is hard to get. It's order n factor. Okay, n factor. Because expectingly it should finish something similar to the some k times the number of permutations of these n elements. So it's in the order of n factors.
Does that mean that for each position in the n, it will have n probability?
Exactly.
For that position.
Exactly, and your probability to get the sorted algorithms after a random shuffle is only 1 over n factor. So as we can see, it's just stupid to doing this kind of stuff. So this sorting algorithm is actually only used in education, and by comparing to this algorithm, we see that how all these algorithms, even the bubble sort, selection sort, insertion sort, are actually working very well. right? So yeah, that's mostly the contents for this class. Any more questions about how these different sorting algorithms work? Because this is our last lecture in sorting algorithm, and from last week we will start to cover dynamic programming. So any more questions?
No.
And how the students from the back?
No.
No? Cool. Great. And I think yeah, so this class usually should be 75 minutes, and we have used 45 minutes of it. And for the next 30 minutes, I will spread some homeworks, and if you have any questions, we can talk about it. So I think that's most of the class today, and thank you.